Welcome to the lecture of Renewable Energy System. In today's lecture, we will talk about the hydropower system and its importance in the society. Hydropower is considered a renewable form of energy because it based on solar energy that drives the hydrologic cycle. The hydrologic cycle refers to the following process. That is, the sun heats water, which take about 97% from ocean. Water evaporates, rises, air current transport water vapor to the upper atmosphere where lower temperature condense vapors into cloud. Air currents move the clouds around the globe and eventually water falls as rain. Through this process, water can reach altitude higher than sea level. The term hydropower means harnessing falling water to produce power. Gravity causes water to descend from higher elevation, creating opportunities to harness water energy, gravitational energy from falling water, and kinetic energy from flowing water. The amount of kinetic energy available from water flow depends on the height from which the water drops, the angle of the slope, and the volume of water per unit of time, that is, the discharge. The energy of flowing water is harnessed by turbines, which are placed in path of the water flow. The force exerted by the water moving over turbine blades rotates the turbine runner. The turbine runner rotates the generator which produces electricity. Historically, hydropower has also been used for milling grains and for water pumping. Hydropower remains the most established, widely used, and long lasting renewable resource for electricity generation. Hydropower installations are often combined with other use, including flood control, the supply of water, and with pumped storage of water for subsequent hydropower. Hydropower can be generated at all scales, that is, from very large gigawatt to very small kilowatt capacity. However, opportunities depend crucially on topographic and rainfall to provide sufficient waterfall. The world's earliest electricity distribution in 1881 derived from hydroturbines of kilowatt scale capacity. By 2008, hydropower capacity had reached about 874 gigawatt, not including 130 gigawatt of pumped hydro storage. The capacity of total worldwide installation continues to increase at about 2% per year, with hydroelectricity supplying about 16% of worldwide electricity as illustrated in this diagram. This proportion may itself increases, driven by consideration of national energy security and the mitigation of climate change. However, environmental and social concerns are often the largest challenges to continue deployment, hence, careful management is essential. Hydropower output depends on annual rainfall, water catchment, and of course installed capacity. Hydropower's theoretical potential includes the total potential energy from all water resources within specified spatial boundaries without any physical, technical, and economic usage limitation. In practice, only a small percentage of theoretical potential can be harvested. Hydropower technical potential is defined as the total energy that can be generated under the technical infrastructure and ecological constraint. Usually, Technical potential ranges from 20 to 35% of theoretical potential. Technical potential is lower than theoretical potential because technical restriction limits, for example, using flood flows for energy production, unless a reservoir with large storage capacity is available, which is not always the case. Therefore, a large proportion of surface runoff remain unused for energy production. Another factor that reduces available technical potential when ecological restrictions are considered is providing a minimum flow of preserved ecologically and socially motivated minimum water condition. This may reduce the stream flow that can be diverted from the main rivers for energy production. Estimated global technical potential for hydroelectricity is 16,400 terawatt hour per year according to USA Energy Information Administration. The EIA technological roadmap for hydropower notes that technical potential corresponds to about 35% of theoretical potential. Hydropower economics potential is defined as the energy capacity that is economically exploitable relative to alternative energy form. Asia has by far the largest hydropower technical potential, followed by Latin America and North America. China has the highest existing energy generation and uses 24% of its potential. In this table, hydroelectric potential and generation for various countries are shown. In general, there is significant unused potential, notably in Africa. In Norway, Venezuela, Brazil, and Canada, hydropower produces more than half of the total electricity. As a country develops, sites with largest capacity are usually harnessed first. So national increase of total generating capacity tend to diminish with time. By the 1940s, the older industrialized countries had utilized their best sites. Now, most of the increase in hydropower generation is in the new industrialized countries, notably China and Brazil. However, national scale estimates can be misleading for local hydropower planning. Since small-scale applications between 10 kilowatts to 1 megawatt are often neglected from assessment despite the sites for such installation being the most frequent. Survey often fails to recognize the benefit for owners of small-scale sites to offset expensive imported power and install long-term capital assets. Thus, the potential for hydrogeneration from run-of-river scheme, that is, with only very small dam, is often underestimated. Social and environmental factors are also important, and these too cannot be judged by global survey but only by evaluating local condition. Hydro installation and plants are long lasting with routine maintenance, for example turbines for 50 years and longer with minor refurbishment, dams and waterway for perhaps 100 years. Long turbine life is due to the continuous steady operation without high temperature or other stress. The turbines have a rapid response for power generation, and so the power may be used to supply both baseload and peak demand requirements on a grid supply. Note that countries using hydropower mainly for peak demand have relatively low capacity factor. Compared with other technologies, the most important advantages of hydropower are the following. Hydropower generation is based on a reliable proven technology that has been around for more than a century, and hydropower plants can be easily rehabilitated or upgraded utilizing recent advances in the hydro technology. Further, hydropower generation is renewable because it does not reduce the water resources it uses and does not require fuel. In most cases, hydropower is an economically competitive renewable source of energy. The levelized cost of electricity is usually in the range of 0.05 to zero point 0.1 US dollar per kilowatt hour. Rehabilitating or upgrading existing hydropower schemes provides opportunities for cost-effective capacity increases. Hydropower exploits domestic water resources, hereby achieving price stability by avoiding market fluctuation. Storage hydropower schemes, such as dams and pump storage, offer operational flexibility because they can be easily ramped up or shut down, creating potential for immediate response to fluctuation in electricity demand. Thus, storage hydros are valuable to meet peak demand or to compensate for other plants in the grid, especially solar and wind, which can experience sudden fluctuation in power output. The creation of reservoirs also allows water to be stored for drinking or irrigation, reducing human vulnerability to drought. Reservoirs can provide flood protection and can improve waterway transport capacity. Further, hydropower plant with reservoirs can generate energy during dry periods and regulate fluctuation in the energy supply network by using the stored water. Also, the environmental impact triggered by implementing hydropower schemes are well known and manageable. Hydropower systems have among the best conversion efficiency of all known energy sources. That is, up to 90% efficiency of water to wire can be achieved. The relatively expensive initial investment is offset by long lifespan together with low cost operation and maintenance. Consequently, the levelized production cost of electricity from hydropower, that is the cost of generation, averaged over the life of the project can be as cheap as 3 to 5 cent US per kilowatt hour under good condition, compared with utilities selling price to the public of 15 to 20 cents per kilowatt hour. One almost unique characteristic of hydropower is the continuous range of applicable scale from less than 1 kilowatt to more than 500 megawatt. Disadvantages of hydropower includes the following factors. It has high upfront investment cost compared to other technologies such as thermal power, but low operational cost since no fuel is required. The environmental issues associated with hydroelectricity are no less controversial than those for other energy sources. Hydrological effect includes the ecological effect and thus the local community. Hydroelectric installation does rearrange the resources, that is, diverting a river into a canal or a mountain stream into a pipe may not greatly change the total flow, but it can have a marked effect on the environment, that is, fall in the water table with well drying up or vegetation dying, etc. And evaporation from the exposed surface of a large reservoir may appreciably reduce the available water supply. The construction process of dam and reservoir itself can cause widespread disturbance with long-lasting effects on a fragile ecosystem. Most obviously harmful effect of a large dam is when it falls or it fails. For example, in 1971 earthquake which severely damaged the lower San Fernando Dam north of Los Angeles had the reservoir been at its maximum height and some 15 million tons of water could have been released onto the 80,000 inhabitants of the valley below. Another issue is silt. Silt is accumulating behind the dam, reducing its useful volume and the hydro potential of the site. In Hoover Dam in USA, Colorado River lost about one-sixth of its useful storage volume in its first 30 years. Another example is Aswan High Dam in Egypt, in which the land downstream and the dam no longer receive the soil and nutrients previously carried by the annual Nile flood, and agriculture system has largely been destroyed to be replaced by irrigation and the use of fertilizer. In the social effects, the most important social effect is the displacement of the people from that location where a reservoir will be placed. The Aswan and Kariba dams involve the relocation of some 80,000 and 60,000 people respectively. The water of the Three George Dam will submerge about 100 towns and displace over a million people. It is estimated that during the second half of the 20th century, some 10 million people were displaced by the reservoir in China alone. Moving water was one of the earliest energy sources to be harnessed to reduce the workload of people and animals. No one knows exactly when the water wheel was invented, but irrigation system existed at least 5,000 years ago, and it seems probable that the earliest water-powered devices was the Nuria as shown in this diagram. The most common description of a Nuria is a water wheel used for raising water from a river so that it can flow by gravity via canal to villages and cultivated lands for irrigation. Today, various types of machine are referred to as Nurias, with difference in structure, power sources, and purposes. Some applies the term Nuria to refer only to the water wheels used to elevate water powered by the flow of a river. Others use the term for a variety of water lifting wheels or devices, whether it is rotated by animal, manpower, or rivers, including those that function as pulley with buckets attached to chains or ropes used for obtaining water from a well where the water table is low. Water wheels come in two basic designs: a horizontal wheel with a vertical axle or a vertical wheel with a horizontal axle. The water wheels can be subdivided according to where the water hits the wheel into the buckshot, overshot, undershot, and stream wheels. The term undershot can refer to any wheel where the water passes under the wheel, but it usually implies that the water entry is low on the wheel, such as shown over here. Overshoot and buckshoot water wheels are typically used where the available height difference is more than a couple of meters, such as shown in the first figure. Undershoot and stream wheels use large flow at little or no head. Overshoot and pitchback water wheel are suitable where there is a small stream with a height difference of more than 20 meters, often in association with a small reservoir. A vertically mounted water wheel that is rotated by water entering bucket just past the top of the wheel is said to be overshoot as shown in figure A. A typical overshoot wheel has the water channeled to the wheel at the top and slightly beyond the axle. The water collects in the bucket on that side of the wheel, making it heavier than the other empty side. The weight turns the wheel and the water flows out into the tail water when the wheels rotates enough to invert the bucket. The overshoot design is very efficient. It can achieve 90% efficiency and does not require rapid flow. Overshoot wheels requires a large head compared to other type of wheel, which usually means significant investment in the constructing the headrace. And an undershoot wheel is a vertically mounted water wheel with a horizontal axle that is rotated by the water from a lower weir striking the wheel in the bottom quarter. Most of the energy gain is from the movement of the water and comparatively little from the head. There are, they are similar in operation and design to stream wheel. The figure illustrates the main component of a hydroelectric generating unit. The generating unit may have its shaft oriented in a vertical, horizontal, or inclined direction depending on the physical condition of the site and the type of turbine applied. This arrangement is a typical vertical shaft Francis turbine unit. You can see that the, the generator is at the vertical position and the water channel is falling through this path over the turbine. This system is said to be vertical because the generator is placed perpendicular to the direction to the water flow. Water is flowing from this side. The main component are the turbine, generator, switch gears this side or at this main transformer and generator transformer as well as the governors and excitation system and control units. Similarly, the arrangement with the horizontal shaft propeller turbine unit is shown in this diagram. The type of turbine selected for a particular application is influenced by the head and flow rate. There are two classifications of hydraulic turbines, that is impulse and reaction. The flow through the turbine is controlled by the wicket gates on reaction turbine, such as shown over here, and by the needle nozzle on impulse turbine. A turbine inlet valve or penstock intake gate is provided for isolation of the turbine during shutdown and maintenance. This is shown over here. Spillways and additional control valves and outlet tunnels are provided in the dam structure to pass flow that normally cannot be routed through the turbine. Synchronous generator and induction generators are used to convert the mechanical energy output of the turbine to the electrical energy. Induction generators are used in small hydroelectric application having capacity less than 5 megawatt ampere due to their lower cost, which results from elimination of the exciter, voltage regulator, and synchronizer associated with synchronous generator. The induction generator draws its excitation current from the electricity system and thus cannot be used in an isolated power system. The generator output is connected to terminal equipment via cables, bus bar, or isolated phase bus. The terminal equipment comprises current transformer, the voltage transformer, and surge suppression devices. The generator circuit breaker and associated isolating disconnecting switches are used to connect and disconnect the generator to and from the power system. The generator circuit breaker may be located on either the low voltage or a high voltage side of the generator step up. The generator transformers step up the generator terminal voltage to the voltage of the power system or plant switchyard. Generator transformers are generally specified and operated in accordance with international standard for power transformers, with the additional consideration that the transformer will be operated close to its maximum rating for the majority of its operating life. In today's lecture, we have discussed the basics of hydropower generation, its advantage and disadvantage. Today's lectures end here. Thank you for listening.